Hi, my name is Jerome. My YouTube channel is Jerome Electronics. This is my first video ever of an animated presentation, so I'm sure it might be a bumpy start, but it is well-intentioned, so please put your seatbelt on and off we go. What you're looking at is a worksheet. I try to give students worksheets where they can find answers to these questions during the presentations. This is just one of 3 for this presentation. This is the second worksheet for this presentation, and this should be the third. And if you can't pull these worksheets from the video, I hope to eventually put them on a website which will be announced later on. Okay, to start out, we need to make sure that students understand what powers of notation are, and so that's kind of where we're going first. The first thing we need to define is something called propagation delay. And so propagation delay is really the time it takes for data to pass through a component. This is a picture of a stoplight, which it runs itself, and one way it could run itself is through logic gates. So these are symbols that represent logic gates, which are the smallest units of artificial intelligence, and you can snap these together, kind of like snapping Legos together. And together they can cause the stoplight to be automated. Probably is done with something called a state machine, which I have another presentation I will be giving for that later on. But for now, just need to understand that each one of these little logic gates, see if I can point to them. This one happens to be a XOR gate, another XOR gate, an AND gate, an AND gate, and an OR gate. We'll be using lots and lots of these as we go through this course. The reason we're doing this in a presentation that has to do with powers of 10 notation is that the propagation delay can be represented as a base number. The base number for propagation delay for a standard digital logic gate is 0.0000000095 seconds. That's 8 zeros after the decimal. That can also be stated as about 9.5 microseconds. And we'll be talking about how to make these conversions in this presentation. Another way to look at it is in clock speed. You'll want to write this down on your note sheet. Clock speed, the definition of clock speed, is the rate at which a computer can perform tasks. The clock speed of a typical personal computer might be 24,000,000,000,000,000 hertz. That's a lot of zeros. It's 11 zeros. And when we're working with such extremely large or small numbers, it's easy to make mistakes. And so to prevent mistakes and make large numbers more manageable, we use something called powers of 10 notation. So when we use powers of notation, we might restate this as 2.4 terahertz. That is cycles per second, which is the rate at which a computer can perform tasks. Miscounting the zeros can be a serious problem, so it's one reason that we use powers of 10 notation. But another reason is that powers of 10 notation is much simpler to read, to understand, and to do math with. So in your worksheet, you have this image, and it needs to be labeled. We have names for each of these different parts of this equation when we use powers of 10 notation. For example, you probably already know that this is the exponent. 10 raised to the 4 is the exponent. The 10 itself happens to be the base. Over on the other side is the coefficient, that is 4.1, and of course I want to make sure that I point out that the decimal is here because the location of the decimal is not always obvious. All right, let's go for another big number. How about the population of the Earth? The population of the Earth on Sunday, May 7th, 2023 at 5:30 p.m., according to this website, was over 8 billion people, right? Well, we can convert this really big number. It happens to be what we call a base number. And we can abbreviate base as just B, but generally we don't use anything at all because it's the number system you've been using since kindergarten, I guess. But there's that many people. Remember, I mentioned that it's not always obvious where the decimal point is because sometimes it's implied. The decimal point for this number is right here. And we can also restate this number if we move the decimal point out of the base location, maybe move it over 3 at a time. We can actually call this number, which is the same value, 8,031,824.849 kilo people, or we could call it K people. K is for kilo. Here we could say, well, it's actually 8,031 mega people, or 8,031 M people, 0.824849. We could move the decimal again. Notice we're just moving the decimal 3 places at a time toward the left. This is 8 gigapeople, or 8 G people. All we're really doing is moving the decimal. Here we go, moving it again into the tera prefix. So it's this many tera people, or T people. Okay. So again, the decimal is located right here. And another thing that we imply, remember the decimal started out as being implied. Nobody wrote it. We just all know where it was. Well, that's kind of the same idea with this times 10 to the 0th power. It is, every number should have a times 10 to the 0th power, but in the base notation system, we don't use it. We just assume that it's there. And of course, 10 to the 0th power, or anything to the 0th power, is 1. If we, fish to the 0th power is 1, and tree to the 0th power is 1. Times 10 to the 0th power is the same thing as saying times 1. And a number that's times 1 is just the number. So that whole times 10 to the 0th power is implied in base numbers. But we have to use it for other numbers. So there it is again. That exponent has a direct relationship to where the decimal is. Power of 10 notation means that the decimal and the exponent actually change together. Every time the decimal moves to the left, the exponent increases by 1. And so I've got this little symbol that helps you remember that. The letter L, if you remember that the letter L points up, it helps you to remember which directions go together. Left is up. You could also do it with a simple upward and left pointing arrow, if that helps you remember. So I am now going to move the decimal to the left, and simultaneously I will be moving the exponent up. There we go. Every time you move the decimal to the left, the exponent increments by 1, moves up by 1. The opposite is also true. If you move the decimal to the right, the exponent should go down. So we can indicate that with a downward pointing R, or also with a downward rightward pointing arrow. When we do that, anytime we move the decimal to the right, the exponent goes down by 1 digit. And that is really kind of the definition of scientific notation. We'll get more into that in a minute. Another thing we need to talk about before we get into scientific and engineering and prefix notation more deeply is how precise do we want our measurements to be? If we measure something like the moon, how far past the decimal do we want to go? How precise do we need this number to be? Well, that's a little bit different for scientific notation than it is for engineering notation. For science, the precision is determined by the person doing the study, the scientist. He decides or she decides how precise they want the precision to be because they're actually making new discoveries. And so they can decide the precision. So any precision necessary to make significant discoveries is good enough. In engineering notation, I tell my students that really all we need is to go maybe 3 digits past the decimal. 3 digits is usually good enough to solve problems and make money. And that's what engineers want to do. They want to solve problems and make money. They're not really going for new earth-shaking discoveries. If they were, they'd probably be called scientists. So the fourth number there, we're going to round it. So that means we're going to drop this number if it's less than 5. But if it is 5 or greater, then we're going to add 1 to this digit. And then we're going to drop this digit. So that's basic rounding. You've probably been exposed to that before, but if you haven't, there you go. That's what you do. Okay? So that is our kind of our standard for my classes for engineering precision. Okay, let's talk about powers of 10 notation. Powers of 10 notation has 3 family members that we really care about. Those family members are called scientific notation, engineering notation, and engineering prefix notation. And so we're going to start with scientific notation, and there are some rules we need to talk about for scientific notation. So to convert a base number to scientific notation, let's pull up a base number. Here's 10425.360. The first thing we're going to do is attach a power of notation to the base number. In other words, we're going to put the times 10 to the 0th power there. And we're going to take note of where the decimal is, because the decimal and the exponents move together. So we're going to move the decimal to the left for this number. And that means left is up. That means the exponent will move up every time we move the decimal left. So there it goes. The exponent changed with each decimal move. There it goes again until there's another rule, and move it until the single digit is to the left of the decimal. The problem is that the digit to the left of the decimal cannot be a 0. So we're going to have to move it backwards. So right is down. We're going to move the decimal 1 digit backwards toward the right. And that's where it should be. The rule is there can only be a single non-zero digit to the left of the decimal. That is the rule for scientific notation. Again, there can only be a single digit to the left of the decimal for a scientific notation number. Now we probably should drop the unneeded zeros. The leading 0 there doesn't change the value, and we need to round this number. We round it 3 digits to the right of the decimal. The 4th digit is a 6. That means that 6 will be dropped, but the 3 will be incremented. It will become a 4. So we're going to round to 3 digits. That means that the number is now 4.254 times 10 to the 2th power. The 2 is the exponent. Okay, so that is how you convert a base number to a scientific notation number. All right, here's another number. We need to convert this one to scientific notation as well. 82350. What I'd like you to do is see if you can do it on your paper, your worksheet, before I give you the answer. So I'm going to give you a little time, not much. you see if you can use these rules to convert this number to a scientific notation number. By the way, I may go faster during this presentation than you're comfortable with, but you can always pause the video as well. So, we're going to convert this base number to scientific notation. We put the power of 10 notation on the base number. Then we're going to find the decimal. It was implied there, so it is located just to the right of the 0. Then we're going to move it so that there's only one digit to the left of the decimal. And every time we move it, we're going to increase the exponent. Next, we can drop the unneeded zeros. There is an unneeded 0 there. The value of this number is the same, whether or not the final 0 is there. And that, of course, takes it to where it's going to be rounded anyway. So this number is converted to 8.235 times 10 to the 4th power. Now convert this one. Remember, the main rule here is that the decimal has to be moved until there is only one non-zero digit to the left of the decimal. That means this time we're going to move the decimal to the right instead of to the left, right? Correct? And right is down. So I'm going kind of slow because I'm hoping you will convert this number to scientific notation before I do. You know the rules. You should be beginning to get the hang of this now. So I put the times 10 to the 0th power on it, locate the decimal, and then I start to make the move. Notice when we go to the right, if we go below the number 0, it's in the negative number range on the Cartesian grid. So the exponent has to be 0 when it's going down, or it has to be negative when it's going down below 0. Drop the leading zeros. Zeros we don't need. The value doesn't change when we do. The answer is 8.255 times 10 to the negative 7th power. Okay. Here's another number. Try this one. Giving you time to see if you can figure out how to convert this number from base notation to scientific notation before I show you the answer. Giving you a little bit of time on your paper. If it's not enough time, you should pause the video. Okay, we're putting a times 10 to the 0th power on it, and then we're going to move the decimal. We know we're going to move the decimal to the left because we need to move the decimal until there is only one non-zero digit to the left of the decimal. That means if we're moving the decimal to the left, the exponent has to increase. So that's the answer. I didn't do it one digit at a time. You're too mature for that. You can actually figure it out. Okay, but we haven't rounded it yet. It needs to be rounded. So hopefully you've rounded it to look like this. Here's another one. Can you convert back to base? Well, that means we need the times 10 to go back to the times 10 to the 0th from whatever it is. In this case, it's a 5. And so we need to subtract and move the decimal to the right until that 5 becomes a 0. So the exponent should go down to get back to 0. The decimal to the right. Had to add another 0 to our placeholder to get the exponent to 0. And once we've done that, we can get rid of the decimal because it's implied, and the times 10 to the 0th power because it's implied in a base number. So that is the official answer there. Now see if you can convert this one back to base. Remember, we're not converting it to scientific notation. It already is scientific notation. We need to convert this one back to base. Since the exponent is a negative number, we need to raise the exponent, right? Well, if the exponent is moving up, according to the symbol on the left side of the screen, up means left. So we're going to be moving the decimal to the left until the exponent is a 0. There it is. Now we can remove the times 10 to the 0th power, and that is because this is a base number, and so that is implied. All right, here's a few more you can try. I'm going to give you a little bit of time to give you a little bit of time to work these out. Probably not enough, but you can pause the video if you feel like you want to work on these without just jumping to the answers. So if you want to pause the video, you should probably do it now because I'm about to give you the official answers. All right, answers. Here we go. The 8125 becomes 8.125 times 10 to the 3rd power. The 0.0006812 becomes 6.812 times 10 to the negative 4th power. The 6405300 becomes 6.405 times 10 to the 7th power. The 0.000031245 becomes 3.125 times 10 to the 5th power. Now, if you are actually working on this, if your brain is engaged in doing this before I give you the answers, you are actually learning. If you're learning, then your brain is making brain cells. That means you are maturing and you are evolving because you got a bigger brain. Try to do everything in all of my videos, presentations. Try to always work ahead of me. And if you do, you will actually learn this and it'll be easier. All right. So we've learned scientific notation. That was it. That's all there is to it. Move the decimal, change the exponent, only one digit to the left of the decimal. Drop the leading zeros, round to 3 digits past the decimal to the right of the decimal, and you've got it. So let's talk about engineering notation now. After that, we'll talk about prefix notation, but right now we're going to focus on engineering notation. Here are the rules. To convert a base number to engineering notation, like this number here, this number 0.6835425.360, we're going to convert that to engineering notation. We do the same thing that we did with scientific notation. We attach a times 10 to the 0th power to the base number. And we're going to move the decimal again in the same direction, but in engineering notation, you move the decimal 3 places at a time instead of 1 place at a time. There's the decimal. We are going to move it to the left, like we did with scientific notation. And there we go, 3 digits. And the exponent was also changed at the same time. It was raised by 3. So really the only difference so far is you're moving the decimal 3 places at a time instead of 1. And the exponent is raised accordingly. We will move the decimal until there are 1 or 2 or 3 digits located to the left of the decimal. So we can move it here because that is 1 digit to the left of the decimal that is a non-zero digit. Remember, there cannot be next to just to the immediate left of the decimal, there can't be a non-zero number there. So we'll drop that leading 0. We'll round the result. And there is our answer, 6.835 times 10 to the 6th power. Now I've tried to go slow so that you could do this before I did, and I hope you did. Okay, here's another number. We're going to convert this base number to an engineering notation number. I've already applied the times 10 to the 0th notation to it, and now we need to move the decimal until there are 1 or 2 or 3 digits to the left of the decimal, and they can't be zeros. So moving it once, back, moving it once. Since we're going to the right, the exponent is going down. Down from zeros into the negative range, it's a -3. Move it again, -6. Move it again, -9, getting rid of all the zeros. They don't change the value of the number, so we can eliminate those. And our answer is 25.36 times 10 to the -9. So there you have it. Now you know both engineering notation and prefix notation. The big difference, prefix notation moves 1 decimal at a time and can have only 1 digit to the left of the decimal. Engineering notation, that moves 3 digits at a time, and that means there can be 1 or 2 or 3 digits located to the left of the decimal. So here's some practice numbers. See if you can figure these out before I give you the answers. I will probably give you the answers. If you just leave this video running, I'll give you the answers before you're ready. So you really should pause this if you really want to learn how this is done. Give yourself an opportunity to try this and own this before I give you the answers. If you haven't paused the video yet, you should, because I'm about to give you the answers now. 8125 becomes, in engineering notation, 8.125 times 10 to the 3rd power. By the way, if you've noticed, that is the same answer if we converted it to scientific notation. Sometimes they're the same, sometimes they're not. 0.0006812 becomes 681.2 times 10 to the -6th power. 640.53000 becomes 64.05 times 10 to the +6th power, and 0.00000031245 becomes 31.25 times 10 to the -9th power. Okay, we've learned scientific notation. We've learned engineering notation. Now we need to talk about engineering prefix notation. To do that, I need to tell you an interesting story. It's an interesting story of a goat and a parrot who fell in love. My students generally refer to this as Chapter 1. Your job is to memorize the entire story. On your worksheet is a table that looks like this, but it doesn't have the colors. And here's the story, and you should write down the words of the story as I tell you the story. Here we go. The goat may kiss Billy, my ugly new parrot friend. I haven't gone crazy. There's a method to my madness. The goat may kiss Billy, my ugly new parrot friend. Now, notice that the goat may kiss are all capital letters, all uppercase letters. Billy is in parentheses and is a lowercase letter. My ugly new parrot friend, all lowercase letters. Now, there's always at least one student in all of my classes that has figured out what I'm doing here. What is the method to my madness? Well, a hint to the method of my madness is in the next row to write down the first letter of each one of those words. So here we go. T-G-M-K. Remember, these are all uppercase letters. B, in parentheses, M-U-N-P-F. Giving you some time to write. Maybe you have a slow pencil today, but a little bit of time. Now, what does this mean? Where am I going with this? Well, in case you haven't figured it out, I'm talking about prefixes. Prefixes that you've heard about. For example, tera, giga. What's the next one? Mega. What's the next one? Kilo. Can you figure these out before I tell you what they are? This next one is base. The next one, M. Some people guess milli, some people guess micro. It's definitely not mega because mega's already been used. This one is milli. Milligrams, millihertz, kilohertz, megavolts, gigaohms. That's what we're talking about. You've heard about these things before, right? The next one. Notice so far, the story of the goat has used the first letters for each one of these prefixes. The next one, U, is micro. Kind of an interesting story because micro doesn't start with the letter U. And I might as well answer this while we're here because some of you are going to go crazy wondering why we use a U for micro. So here's why. The Greek letter M looks like a U. We don't have a Greek letter M on our keyboard, but since it looks so much like a U, scientists and engineers and other lazy people have decided that we'll just use the U key. But that's a Greek mu, and it looks really close to a Greek M. And we've already used the other two kinds of M's, the milli and the mega. We've used big M for mega, little m for milli, and so now we have one more word that has an M. We're using the letter U because that looks most like a Greek letter M. Now, there is a test on this, at least for my students. There's a test on this where you fill out this entire table without any help. Your job is to remember everything on this table. Micro. How do you make sure you remember that micro and milli are in the right place? Because a lot of times students mix up milli and micro and they put milli under my or micro under my and milli under ugly. And so how do I remember these? I remember them that micro is alphabetically before milli. And if micro is alphabetically before milli and you put it before milli, then it's wrong. I'm sorry, I don't have a better way to remember that, but it's milli first, then micro in non-alphabetical order. Okay, what does N stand for? Right, nano. P, what does P stand for? Yep, pico. And F, you all got it right. Femto. It's femto. There's one line that's left there. The last row of this table. It's important, but it's easy. Down in this row, I want you to write times 10 to the 12th power is the same thing as tera. Times 10 to the 9th power is the same thing as giga. You can either say giga or you can say times 10 to the 9th power, right? Now, if you compare those two exponents, you can see a pattern forming, and you can fill out the rest of this last row before I tell you what it is. Can you do it? It's always times 10, and then you just reduce the exponent by 3. So the next one is times 10 to the 6th power, times 10 to the 3rd power, times 10 to the 0th power, times 10 to the negative 3rd power, times 10 to the negative 6th, times 10 to the negative 9th, times 10 to the negative 12th, and times 10 to the 15th power. Okay? So, if you can remember that story, it's pretty simple to remember the rest of this table. And you will need this table to make engineering prefix conversions. Okay? So if you can memorize this table, you got it. The goat may kiss Billy, my ugly new parrot friend. If you can remember that mnemonic, you own this whole concept. And it's pretty easy if you do it that way. Okay, so we're going to take these engineering prefix numbers, we're going to convert them to engineering prefix numbers. From engineering to engineering prefix notation. Okay? So I'm going to show you how to do it. You're going to realize it's easy. I hope you will go faster than me and work ahead of me and see if you can figure these out before I tell you how to find the answer. I'll show you the first one, see if you can do the next one before I tell you the answer. So what if you start with a base number? If it's base, first convert the base to engineering notation. We just went through that. You know how to do that. But once you've done that, then you're going to convert engineering notation to prefix notation. So we're going to look for this on the chart. We're going to trade it for this. And that's our answer. That's engineering prefix notation. It's that simple. Can you do the next one? Do this one. And finally, do this one. So again, first, if you're given a base number, convert it to engineering notation. Then trade the times 10 to whatever exponent it is for the letter, the prefix. In this case, it was an N, and you're done. You could also, instead of just saying N at the end of this one, you could say nano as well, and it would still be correct. So that's how you convert engineering notation into prefix notation. Now, we need to say something that in the past has been confusing to my students. There are also units, and units go at the very end of the statement, at the end of the value. You need to be careful that you don't confuse units for prefix. Units could be, units are not prefix. Unit, the prefix comes before the unit, and units are actually, they tell us what we're talking about. So on your worksheet, fill in the top of this table as quantity, quantity symbol or Q symbol, unit, and then unit symbol. You have already been exposed to this information before. If you've had any math classes at all, they're always telling you, Don't forget to use the units when you give your final answer. The final symbol represents the unit, and the unit actually tells us what we're talking about, right? If I say how many, or if I say what is the length, that would be the quantity that we're looking for. What is the length? We're quantifying something. What's the length of your shoe, for example? If you measure your shoe and it's 12 inches long, those are the units. The length is the quantity. The units are the description of the quantity. Okay? So we have something called current. We also call current amps, and we also call current and amps amperage. Current, amps, and what's the other one? There's a third one. It'll come to me. Intensity. There's the symbol. Current, amps, intensity. Those all are the same thing. When we say what's the intensity of the circuit, we're asking what is the amount of current that's flowing through the circuit, and we're asking about what is the amperage of the circuit. The symbol for the question, what is the current, is I. What's the intensity? The unit is the ampere. And just as length was not interchangeable with the word inches, current is not technically interchangeable with amps. Current is how you ask the question. Amps are the units you give to answer. They have a symbol for amps. Amps, amperes, current, intensity, all the same thing. The symbol, if you're giving the final answer, the units are A. For voltage, V. Now, this is technically incorrect. It should say electromotive pressure or electromotive force. The quantity should be electromotive force, electromotive pressure. The symbol should be E, and sometimes it is. You will see that I use E sometimes. Why am I putting a V here for both the question and the answer? Well, it's because electricians and electrical engineers, they're lazy. They want to say volts, and they want to say volts, and they say volts, and it's bad grammar, but everybody accepts it. So, resistance. If I were to ask what is the quantity of the resistance, I would say, I could abbreviate that by saying what is the R? R equals, and then I would say ohms. The unit is ohms. And there's a nice symbol for that. That's a Greek symbol, the omega. Omega. Why are we using omega? Because that is very close to the word ohm. Why are we using the word ohm? Well, because the relationship between volts and amps is resistance, and that relationship was discovered by a man named Georg Ohm. Volts was named after a guy named Volta. We'll talk about that. Ampere was a guy's last name. We'll talk about all of those later on. But the unit is not the same thing as the quantity name. And in most cases, with voltage, we kind of let that one slide. Frequency. That's a little f, not to be confused by femtos F. And frequency was named after a guy named Hertz. And that's why we use Hz, but another way to say that is CPS, or cycles per second. Just another way to do that. Then there's capacitance, which is a capital C for the quantity, named after Michael Faraday. And so basically the unit of capacitance are farads, and the unit symbol is F. Inductance, L. Don't know why. I have to look that up someday. And the guy's last name was Henry that we named it after, and of course the unit of induction, or the unit symbol, is H for Henry's. And there's power. Power, P, but power, the units of power are watts, named after James Watt. And of course we can use W for watts. Now these aren't all of the units. these are just the common ones that we'll be using a lot in this class. So in this course. So the whole point here is not only am I introducing a lot of the units, but you need to realize that units are not prefixes. You need to make sure you don't confuse the prefixes with the units. And how do you know? Well, prefixes will be listed if they're not a base number, but they won't be the last symbol. The last symbol is always the units. So hopefully you understand that. All right, so let's practice. Convert these numbers. This is a base number, and you want to convert it first to engineering notation, and then you want to convert it from engineering notation to engineering prefix notation. Remember, first convert the base to engineering notation, then convert the engineering notation to prefix notation. Now, I think most of you understand this well enough by now that you can do this faster than I can give you the answer. But I'm also going a little bit slow so that you can, because if I just give you the answers, you don't learn anything. But if you can get the answer before I do, you own this. So do your best on your worksheet. Figure these out before I tell you what the answers are. Okay? So this one. Well, I've got to move the decimal 3 places at a time. I'm going to move it to the right. That means the exponent's going to go up. So the decimal will go over 3 places to the right. That's 4.7 times 10. And, the R pointed down. We went to the right. R points down. That means we're going 0, down 3. So the answer for this one will be 4.7 times 10 to the negative 3 volts. Right? And now all we have to do is find that 10 to the negative 3 on the table above. And then we realize that's milli. So it's 4.7 millivolts. Not so bad. Do this one. That is 6 zeros. And the decimal is not shown. It's implied. It's at the right side of the number. Just pausing for a moment so that you can take a shot at getting through these. I think I actually listed these problems on your worksheet, so you could actually just start cranking through the answers if you want. I mean, if you own this, you're ready for the test, right? Okay. So we're going to move the decimal to the left, and left is up, so the exponent that we're going to slap in there is going to go up. All right, so the decimal has moved 3 places at a time twice. So, and you can have 1 or 2 or 3 digits to the left of the decimal, which we have. But since everything else was a 0, we could drop all of those zeros and go with times 10 to the 6th power. And times 10 to the 6th power is a mega value. So 778 mega ohms. If you got that right, you are owning this. Here's another one. Moving the decimal 3 places. This time we have to move the decimal to the right. And we can't just stop at the end of the zeros because there can't be zeros to the left of the number. It has to be actual digits. So what will happen here is you're going to move the decimal 9 places to the right, and right is down, and down from 0 is a negative number. So the answer is going to be 497 times 10 to the negative 9 farads, which, if you look on the chart above, the goat may kiss Billy, my ugly new parrot friend chart, you'll see that negative 9 is in the nano range. So the answer is 497 nanofarads. One more. 9,900 hertz. Decimal is implied on the right side of the number. Moving that decimal 3 places to the left will cause the exponent to go up because left points up. The answer then in engineering notation is 9.9 times 10 to the 3rd power hertz. The equivalent of that is 9.9 kilohertz. If you did that, you got it right. One last one. Going to move the decimal 3 places at a time to the right. Right points down. The decimal, the exponent. The exponent will go down 3 places at a time. We're going to have to move that decimal 3 and 6 places, and then we'll have 2/3 to the left of the decimal, 0.2. Since we moved the decimal 6 places to the right, we went down 6 values from 0 to 33.2 times 10 to the negative 6, which is equivalent to 33.2 microamps. Okay, one more thing that you need to know how to do, one last thing that you need to know how to do is how do you convert these examples of prefix notation to other forms of prefix notation. So we're just converting one prefix to a different prefix, really. To do that, we're going to convert 4.7 millivolts to microvolts. Here's how you do it. First of all, you take what it is. You circle that. And from there, you go to what you want. Now, to get there, you got to move. Every time you move a prefix step, there are 3 decimal moves. So we're going from times 10 to the negative third to times 10 to the negative 6, right? So 3 moves in the same direction. We're going from milli to micro. We're making 3 moves in the same direction. Okay. So there's 1, there's 2, there's 3. Once we have made that move, those 3 decimal moves, it has been converted to microvolts from millivolts. Okay. Next one, we're going to convert 778 mega ohms to its equivalent in kilo ohms. Just going to pause for a minute while you work ahead of me and figure this out before I tell you the answer. If you got that answer, you understand this and you own this concept. Let's do the next one. 497 nanofarads. Going to convert that to millifarads from nano to milli. We're starting at nano. We're moving to milli. So we've gone from nano to micro to milli. That's 2 columns we've moved. That means we need to move the decimal the same direction that we moved above in the table, 6 places. 3 places per hop. So 1, 2, 3, 4, 5, 6 places, and we're done. 9.9 kilohertz. Let's convert that to megahertz. We've got K for kilohertz. That's there. Where are we going? We're going to mega, I said mega, didn't I? Milli, going from kilo to milli. That's actually 2 moves. So we're going to the right 6 times. 1, 2, 3, 4, 5, 6. And that's the answer. Okay, with this last one, we need to convert 33.2 microamps to base. So, micro. To get to base, we need to go 2 columns. Every column is 3 decimal moves in the same direction. So we got to move that decimal 6 places. 2 columns times 3, 6 places. 1, 2, 3, 4, 5, 6, and we've got it. That's all there is to it. Think back now. What have we just learned? You've learned how to convert base numbers to scientific notation numbers by moving them one decimal at a time until there's one non-zero digit to the left of the decimal. Then with engineering notation, we moved it 3 places at a time. And then with prefix notation, we just traded the times 10 to the whatever exponent to its equivalent prefix. Then to convert from one prefix to another, we just moved on the table. Every time we moved to a different row, it meant that we needed to move the decimal 3 places in the same direction. Once you own that, you own this whole idea. And now you know. Your brain got smarter. You've evolved.